Hi everyone, welcome to my third project demo. In this video I would like to present my third end-to-end data engineering project called Recommender System Data Platform. This project simulates a production-oriented backend platform for recommendation system. And the main goal of the project was to design and implement a scalable data platform capable of ingesting large volumes of product, metadata, and user reviews, processing structured and semi-structured data, building ML-ready feature tables, generating text embeddings. So we have two separate pipelines in this solution, preparing data for downstream recommendation models and vector similarity search. And the project combines multiple areas of modern data engineering and data ops, including batch processing, medallion architecture, and data lakehouse approach with Apache Iceberg data format, distributed computing with Apache Spark on AWS Elastic MapReduce, some orchestration with Apache Airflow, data quality check with great expectations, some vector and NoSQL databases, in this case Pgvector and MongoDB, some containerization with Docker and AWS Elastic Container Registry. Once again, infrastructure as code approach with Terraform and cloud native processing, once again on AWS cloud with services such as S3, Glue, and Postgres database on RDS. And the final result is a production-oriented data platform that prepares structured ML-ready dataset and semantic vector embeddings for recommendation and retrieval systems. Although this project is focused on recommender system, the same architecture could also be reused for other AI-driven use cases. And the core idea is basically the same: ingest data from multiple sources, structure and text data, so semi-structured. Clean and transform it, generate embeddings, store them in a vector database, and make them available for downstream AI application. And the most natural alternative use cases, well, first of all, RAG or AI agent for some company. Well, basically, the current pipeline already contains the core components required for a RAG architecture. Components like data ingestion from multiple sources, text processing and cleaning, embeddings generation, storing embeddings in vector database, in this case, as I mentioned, Pgvector, semantic search capabilities, Airflow orchestration, and data quality validation. And the only thing that would need to change in the type of input data. Instead of product reviews like in this project, the platform could process, for example, some company documentation, some internal policies, procedures, product descriptions, some, I don't know, support tickets or sales notes. Additionally, some emails, PDFs, some knowledge base articles, white papers, and so on. So basically, companies' knowledge stored in different kind of documentation. And in that scenario, Pgvector would become the knowledge base for an AI agent, for example, answering employee or customer questions. And some other alternative use cases could be enterprise knowledge search, as I mentioned, but also some customer support automation, customer opinion monitoring, and so on. So a lot of different use cases, but in this demo, I will focus on recommendation system. So let's start. Okay, business problem. Let's assume that this platform is used by some large global e-commerce company. Basically, the company sells millions of products and generates massive amounts of both structured, semi-structured, and unstructured data every day, including product metadata, some customer reviews, user interactions, support tickets, and behavioral events. And over time, the company realized that this traditional recommendation system based only on ratings or historical interactions were no longer sufficient. And that's why the business wanted to build more advanced AI-driven solution, which will be capable of understanding customer opinions, supporting personalized recommendations, performing semantic search, and providing a foundation for future AI agents or RAG systems. And however, building AI solutions require much more than training only machine learning or deep learning models. And this is like a real world problem, because recently I read this Ernst & Young report called How Polish Companies Implement AI. And according to this report, one of the biggest barriers in AI adoption in Polish companies, but I think it is like a global problem. It is not AI models themselves, but immature data engineering foundations, fragmented data platforms, and poor data quality. And this report also shows that, for example, only 9% of Polish companies have data fully prepared for advanced AI systems. And the worst part is that many organizations still even do not fully understand the quality and availability of their own data. So a lot of work to do for data engineers in this area. This project was designed as a practical response to this kind of challenges. And instead of focusing on recommendation model itself, it's the job for data scientists and machine learning engineers. The goal was to build a scalable backend data platform that prepares high quality data products for modern AI and recommendation systems. So basic business challenges. This platform addresses several common challenges faced by modern e-commerce companies. First one is integrating data from multiple heterogeneous sources. data in different formats, structured data, semi and unstructured data. So the next challenge is that this modern e-commerce companies are processing large volumes of structured and semi-structured data. Another challenge was preparing reliable ML-ready data sets. So something like feature stores. Next, generating semantic embeddings from customer reviews. And last challenge was that this platform should enable scalable AI-driven recommendation and retrieval system. Okay, what about main stakeholders? Well, such platform could be used by, for example, product managers, marketing and sales teams. So recommendation system based on understanding what customer think about the products. It's like every product manager or marketing team dream, I think. And of course, other main stakeholders are data scientists and machine learning engineers. Okay. The prepared data products can later support some recommendation engines, semantic search, AI shopping assistant, and RAG-based application. So to sum up. Okay. What about platform requirements? To support this business goals, this platform should first of all ingest and integrate data from these multiple available sources, then process data at scale using distributed computing, because these are big data volumes, and it should be big data solution. Then this platform also should automatically validate data quality, since good data quality is crucial for AI use cases. This platform also should generate ML-ready feature tables and vector embeddings. It also should support incremental processing. And last but not least, this platform should provide a scalable, cloud-native, and production-oriented architecture for some future AI workloads. Okay, so that's enough about requirements, stakeholders, and challenges. Now let's see this system architecture. Okay, so now let's look at the architecture of this project. This is the system diagram. It's not so fancy as the previous one, but still. Okay, the architecture in general follows lakehouse oriented approach, and the platform is divided into several logical layers. Let's start with the source systems. Let's zoom in a little bit over here. Okay. The project in general processes two types of data. product metadata and user reviews. The original datasets come from Amazon reviews datasets over here. Maybe let's zoom in a little bit once more. Okay, and to simulate real production environments, I have created actually two different source systems, two different databases. So Postgres database for structured data, so metadata, product metadata, and MongoDB database for reviews. And this allowed me to simulate heterogeneous enterprise data sources. The first source is Postgres SQL database hosted on Amazon RDS, and it stores structured product metadata such as product title, category, brand, and some project attributes. And the second source, I have created MongoDB database, and it stores semi-structured review documents, so JSON documents containing review text, summary, some ratings, some time steps, and some verification information. And this architecture simulates real enterprise systems where data usually comes from multiple sources. And then we have two pipelines in this solution. The pipeline then loads data into the S3 based data lake and processes it through multiple layers. So we have row layer over here, then some staging layer over here, and then ML ready layer over here. And the final outputs of the platform are ML ready Iceberg featured tables and vector embedding stored in PostgreSQL with Pgvector. And then those outputs could be used by some ML models, some analytics, and of course recommendation system. So let's start with row layer over here. So basically the ingestion pipeline loads raw data from this simulated databases into Amazon S3. And the row zone stores original source data in append-only format. We can check my S3 cloud. Here you can see once again I have a bucket for this project, for this system, and inside this bucket we have once again three prefixes: row, staging, and ML ready. Let's see the row layer. Row layer data inside this row layer is divided or partitioned by data source, so separate prefix for product, separate prefix for reviews. Let's check, for example, products. So we have two ingestion over here. Let's see this one. So we have this row JSON-L files or documents over here, and the pipeline also generates a JSON manifest file. We can see it's over here. Let's open it. And these manifests contain metadata about this particular ingestion process, such as some ingestion time step, right? Source information over here, some processed files over here, some destination like bucket name, prefixes, and format. So some batch and also some batch metadata. So for example, number of ingested records over here, right? So simple JSON-based manifest for every ingestion process. Okay, and this improved traceability and reproducibility of this solution. Okay, let's go back to architecture diagram. Then we have this staging layer over here, and this layer is processed with PySpark, as you can see here, on AWS Elastic MapReduce serverless application. And at this stage, the pipeline standardizes schemas, validates data, normalize column names, clean records, and it converts raw JSON data into Parquet format, and then data are stored in this staging layer as Parquet files. And this layer separates raw immutable data from cleaned analytical data sets. Then we have ML ready layer over here, and in this layer uses PySpark once again for some transformation, Apache Iceberg as a data storage format, Glue catalog also, and Amazon S3, of course, for storing those data. And as I mentioned, the system creates Iceberg tables, so 4 different ML ready Iceberg tables, and we can check S3 once again. Let's see this ML ready prefix, ML ready database, and as you can see here, we have 4 Iceberg tables, like product features, user features, user product interactions, and some global stats. And these tables contain engineered features that can later be directly consumed by recommendation models. And let's go back once again to this diagram. And this was the first pipeline which processes this structured table product metadata, but there's also another pipeline in this solution, Embeddings pipeline. And this is like one of the most important part of the project is this embedding pipeline, and this pipeline generates semantic vector embeddings from review text. And the pipeline first prepares and filters review over here, review text data. Then it uses sentence transformers to generate embeddings using the model All Mini LM L6 version 2. processed by Elastic Map Reduce serverless application. And then the generated embeddings are loaded into this Postgres with Pgvector support. Okay. Of course, there are some additional features of this solution. For example, Airflow orchestration. So the entire platform is orchestrated with Apache Airflow as a sequential DAG. And well, Airflow controls all stages and all parts of the solution. So ingestion, some Spark transformation, validation tasks, embedding generation, Pgvector loading, and some final validation over here. And as I mentioned, the DAG executes tasks sequentially. Well, I did it to avoid Elastic Map Reduce resources contention, and it simplifies orchestration as well. Okay. Another additional feature is data quality checks or data validation. So this project also contains multiple data quality mechanism, and this validation is performed using great expectations, but also some SQL validation checks and some Python custom validation scripts. And this validation is executed after staging transformations. So over here, so validation results stored as JSON. Then validation is executed after ML-ready table generation. So over here, and also after embeddings loading into the Pgvector, we have some validation. And validation results are stored as JSON artifacts. I will show you these artifacts in implementation part of this video. And of course, all infrastructure, all cloud infrastructure in this project is created via code with Terraform. So it can be versioned, it can be automatically deployed, and I don't know, scale up or scale down if necessary. Of course, we have some GitHub Actions CI workflows as well, which automatically validates some code in this solution. Okay, I think this is enough about the system. This is how this system looks like in big picture, and this is how it is designed. And now let's see some implementation detail of this data platform. Okay, so before I will show you the code and implementation details which creates the system, I would like to discuss the engineering challenges I had to deal with in this project. Quick info about repository. Like in the previous projects, the repository is organized into several key folders. And those folders reflects this system architecture once again. Okay, so engineering challenges. Basically, this project focuses heavily on production-oriented architecture and scalability. So there was a lot of different engineering challenges. I will point out just few of them, and I shortly discuss how I try to solve them. Okay, so the first challenge was designing a scalable distributed processing environment, since this is a big data solution, but without managing Spark clusters manually. So I decided to use AWS Elastic MapReduce serverless. And this is because, well, first of all, it supports distributed Spark workloads. Then compute resources scale automatically. Well, there is also no need to manage clusters manually, and well, compute is separated from storage. And this architecture improves scalability and cost efficiency. Basically, the project stores data in S3, while compute resources, AWS EMR, well, they are provisioned only during execution. And this is like a key characteristics of modern cloud native data platforms and foundational principle of every big data architecture. So separating storage from compute. Okay, another challenge was building a lakehouse architecture capable of supporting ACID transformations, some schema evolution, and some scalable analytical processing on top of S3 storage, not some data warehouse. And the ML-ready layer, as I mentioned before, uses Apache Iceberg tables. Why Iceberg? Because, well, Iceberg provides some important lakehouse features such as ACID transformations, schema evolution, partition management, some snapshot isolation, and some scalable data handling. And because of that, the project architecture follows the lakehouse principles. So to sum up this challenge, this platform combines low-cost object storage in S3 with warehouse-like transactional capabilities where data are stored in S3. Well, one thing worth mentioning is also that these Iceberg tables are registered in Glue catalog once again, so they can be queried through AWS Athena, for example. Okay, next challenge, third one. This third challenge was minimizing unnecessary recomputation and enabling efficient processing of continuously growing data sets. So basically, this ingestion layer in this project uses append-only loading into the raw zone in Amazon S3, and each ingestion batch is stored in a dedicated partition based on ingestion date. And this solution improves traceability, scalability, and reproducibility. And on the other hand, this embedding pipeline additionally use incremental logic based on review identifiers, text hashes, and model versions. So before generating new embeddings, the pipeline checks whether a given review was already processed and whether the review content was even changed, for example, right? And this prevents unnecessary recomputation of embeddings, and so significantly reduces processing costs, for example. Yeah. And one additional feature about this third challenge is that this ML-ready layer also operates on partition datasets stored in Iceberg tables, as I mentioned, and this improves incremental reads and scalable analytical processing. And this challenge was especially important because this platform is designed to work with large-scale recommendation systems where data sets continuously grow over time. Every this like global e-commerce platform had to deal with new reviews and new product data or metadata every day, every hour, or even every minute. Okay, fourth challenge, and this was one of the biggest one, and to tell the truth, most annoying. One of the biggest engineering challenges in this project was deploying this Embeddings pipeline into cloud environment. Because initially I tried to execute the sentence transformers pipeline directly on EMR serverless using standard Python dependency packaging. Well, but it didn't work because this caused multiple production-like problems such as dependency, conflicts, Python version, mismatches, missing libraries, some package size limitations, and environment instability. So, well, at one point, jobs failed because, for example, Spark executors could not correctly access the required NLP dependencies, for example. So, to solve these issues, I had to redesign this whole Embeddings runtime architecture and whole Embeddings pipeline. To solve these problems, I created a custom Docker image based on official EMR serverless Spark runtime. And this image, I will show you this image later. Well, it installs all NLP dependencies, it preloads the embedding model, configures environment variables, and store the project source code inside the container. And then the image was then uploaded into AWS ECR, so Elastic Container Registry. I can show you this service. Moment. Elastic Container Registry over here. And I have like one private repository, recommender embeddings, and inside this repository I have this image over here, right? So to deal with this challenge, finally I had to create a dedicated EMR serverless application for embeddings workloads using this custom Docker image. So I have two EMR serverless applications in this solution. I will show you that. This is EMR serverless, not a cluster on EC2. Manage applications. And as you can see, Here I have two applications, one for tabular data transformation with Spark, and one for this embeddings pipeline over here. Right. Okay, let's go back to presentation. Well, to sum up this challenge, this solution significantly improved once again reproducibility, dependency isolation, runtime stability, and this deployment consistency. And as I mentioned, this was like one of the biggest challenges for me personally, and it was one of most valuable engineering lessons from this project. Okay, next challenge. Another challenge was orchestrating multiple resource intensive Spark jobs in some cost-effective and stable way. Well, my Airflow DAG executes tasks sequentially, but this decision was, intentional. Why? Because the project, prioritizes stability, cost optimization, and some predictable resource usage, right? Runtime multiple, heavy Spark jobs simultaneously could increase EMR costs and create some resource contention once again. On the other hand, sequential orchestration simplified this DAG management and improve reliability. Okay, and one last engineering challenge. This one's also practical. Practical engineering challenge was local development environment. My local development environment. Well, basically Apache Airflow, when used on my local laptop on Windows, caused multiple compatibility and stability issues on my native Windows environment, especially around dependency management and orchestration tooling. And because of that, finally, the project was developed using Ubuntu Linux, and this provides more stable and production-like environment for Airflow, for Python virtual environments, for Docker, and for some Spark-related tooling. So I use Linux in this particular project. Okay, I think that's enough. 5 main engineering challenges. Now let's see how this solution, how this system was created. I will show you some code. Okay, so code walkthrough, and in this part of the video, well, I will not focus on standard components of the system, such as basic ingestion scripts or Terraform infrastructure or some simple ETL transformations. Well, because those elements were already discussed in detail in my previous projects or previous videos. And instead, I would like to focus on the parts of the platform that make this project more unique from an engineering perspective, and better demonstrate production-oriented AI and data engineering challenges. So I will briefly present 4 selected components of this solution. First, a short example of MongoDB ingestion used to simulate semi-structured enterprise data source. Then an Airflow DAG responsible for orchestration, the entire platform, And then Docker and ECR runtime architecture used for embeddings generation, and finally some PySpark embeddings pipeline, actually some part or stage of PySpark embedding pipeline. Okay. Well, these components best demonstrate the most important architectural engineering decisions, which I had to implement in this project. Okay, so let's start with the first one. So MongoDB data source. Well, in this project, you have to remember MongoDB was used to simulate a semi-structured enterprise data source, containing customer reviews. Why? Because this approach better reflects real production environments where organization often work with some heterogeneous systems and different data formats. Okay, so here we can see this is my VS Code, and see here in source code folder we can see data sources, MongoDB, and here some JavaScript for setup recommender database in MongoDB. So basically it's a simple initialization script responsible for creating a database, creating a collection, inserting a sample Amazon review document inside this collection. Basically collection it's a like a equivalent of table in normal SQL or SQL database. In MongoDB it's called collection, and inside this collection we have a series of JSON or JSON documents. So there are no rows with strict predefined schema, but we have JSON documents, and every document can have different schema, for example. Okay, so this simple script first switches to recommender database and creates the reviews row collection, right? Then it inserts a JSON review document containing both structure and semi-structure fields. So this part of the script, and these fields are, for example, ratings. It's called overall over here, review text, some, for example, reviewer name, some summary, some timestamp, and some reviewer metadata, and also some product identifiers like this ASIN, I think, number. And basically this structure is much closer to real world document oriented data sets than some traditional relational tables. And finally, here at the bottom of the script, the script verifies the insertion by counting documents which are inside this collection and displaying some sample review document, right? Okay, so this MongoDB collection later becomes the source system for this ingestion pipeline, loading review data into S3 row layer. So a simple Java JavaScript. Okay, now let's move to the second script I would like to show you. So Airflow DAG, and I will show you how I orchestrated these pipelines and this whole system. Okay, so basically over here. Airflow DAG is defined in this recommender system pipeline product Python script over here. Let's move to the beginning. This is one of the most important components of the entire system because well, it orchestrates the complete end-to-end data pipeline or even data pipelines. First, we have some library imports. Then over here, on the top of this file, we can see the default configuration shared by all tasks in the DAG. It defines basically the common execution settings, such as task owner over here, retry policy, failure notification, and basic error handling behavior, while ensuring consistent execution across the entire pipeline. Then we have some global configuration of the platform over here. And this part defines EMR serverless application, for example, some S3 bucket, and basically S3 URLs and S3 locations, but also some runtime configuration, some Spark jobs, and some shared environment variables. Well, one of important architectural decision was separating the standard Spark workloads from embeddings workloads. And because of that, the project uses two independent EMR serverless applications. I show you those applications. So one for standard distributed Spark transformations, and another one dedicated to Docker-based embeddings generation. And this separation improved runtime stability and some dependency isolation. Next, we can see two separate Spark runtime configurations for those two applications. Well, the first configuration is used for standard PySpark jobs. So this one over here, and these jobs run on this standard EMR application. These are, for example, staging transformations of feature engineering and ML-ready table generation. And then we have the second configuration, and it is dedicated especially for embeddings generation. So this part of the code over here. And here we can see some custom runtime settings for example, Docker execution, offline Hugging Face, for example here, right? Inference, some cached embedding models, environment variables, and NLP batch processing, for example, batch size over here. And this configuration was necessary because the standard EMR dependency packaging approach, as I mentioned before, caused multiple runtime issues during deployment. So basically, these parts of this DAG is these are different configurations. Okay, then next section contains local Python wrapper functions for all tasks in this DAG over here. And it was like another small design decision in this system. I use lightweight Python wrapper functions for every task. So for ingestion, for validation, right? For loading data into Pgvector, for example, and so on. And the purpose of this Python wrapper functions was to keep the DAG focused on orchestration while separating the business logic into the reusable modules. The actual, validation and ingestion logic is implemented in dedicated Python scripts over here in source code. And that making the code easier to maintain, to test, and reuse outside of the Airflow. And as you can see, for example over here, these wrappers also use something what is called lazy import. So the required modules are loaded only when a task is actually executed, and this reduces, the overhead of parsing the DAG. So to sum up this part, these wrappers are responsible for ingestion, validation, loading embeddings into Pgvector, and orchestrating local Python-based tasks, because not all tasks in these two pipelines are executed by this EMR, AWS EMR applications. Some lightweighted tasks are executed locally, for example. Yeah, and once again, this approach improves modularity and keeps orchestration logic separated from actual business logic. So okay, so these are wrappers, and then finally we have this DAG definition. It starts over here. We can see different parameters here. One, of course, like DAG ID, default arguments. Like okay, here, these are these arguments from this dictionary from the beginning over here. And one important and worth mentioning, I think, parameter is catch up. So this one set to false. And this tells Airflow not to automatically execute missed historical DAG runs, right? Starting from the start date. I have the start date over here, but I don't have defined schedule. And this set of parameters causes that instead of the pipeline only runs when it is explicitly triggered, which is a desired behavior in this project, because I don't want to pay for running this DAG and compute these tasks on EMR every, I don't know, day, on every week. And then this DAG itself is divided into 4 logical phases. Phase 1 is row ingestion and staging transformations. As you can see, we have some Python operators for local execution and some EMR serverless start job operators over here. Of course, at the beginning we have empty operator, and at the end we have as well the empty operator. And this phase 1, basically the system ingests product data from PostgreSQL, ingest products, for example, ingest review from MongoDB, transform raw JSON data into clean data Parquet data sets. Also, we have transform task, transformation task, validation task, and then we have ingest reviews, transform reviews, and validate staging data set using great expectations. Once again, for example, over here, validate reviews. And this stage finally creates standardized analytical data sets inside this staging, so second layer. Then we have phase 2, so ML ready feature engineering. And the second phase builds ML ready Iceberg tables, and this includes product features, so build ML ready products task, and then validate ML ready products, build ML ready users, so user features, then once again validate ML users, then build ML ready stats and validate them over here, and last task build ML ready interactions and validate these interactions. So to sum up, each feature engineering step is followed by a dedicated validation task. And well, this validation task improves data quality and reliability of downstream ML workloads. Then we have phase 3 over here, and we have some tasks inside this phase as well. And this third phase prepares review text data and generates vector embeddings. So this is like this second pipeline, and then it is using sentence transformer. And this is one of the most computationally intensive part of this platform. And this embeddings job, this is prepare embeddings and this is generate embeddings. And this embeddings job uses Docker-based runtime execution, as you can see here. Custom EMR configuration and dedicated Spark resources allocation for both driver over here and for executor over here. And this generated embeddings later become the semantic layer for the recommendation platform. Okay, and phase 4. So this is quite long DAG. This is like a vector serving layer, last one. And we have, well, basically 2 tasks over here. So finally, the platform loads embeddings into the PostgreSQL with Pgvector support. Right, load review embeddings to Pgvector, for example, and validates the final vector serving layer. So Python operator with Python callable validate Pgvector wrapper over here. And then at the end we have this once again empty empty operator. And at the end, at the bottom of this DAG, you can see over here the final orchestration logic defining the entire sequential, so one by one execution flow of this platform. Okay. And what else? Well, as I mentioned before, the tasks are intentionally executed sequentially. Why? Because this decision prioritizes operational stability, simplify debugging, and cost optimization for EMR serverless workloads. Yeah. Okay, to sum up this long script, long DAG, this DAG demonstrates how the project combines orchestration, distributed processing, validation, and the second pipeline, so embeddings generation and vector serving in one, I hope, production-oriented end-to-end data platform. Okay. Now let's move to third scripts or third part of implementation I would like to show you. So Docker and ECR runtime architecture. Let's close this one. And here we have Docker with Dockerfile. Okay, so here is my Dockerfile. As I mentioned before, initially I tried to execute the Embeddings pipeline directly on EMR serverless using standard Python dependency packaging. However, this approach caused multiple runtime problems such as dependency conflict, package size limitation, and unstable executor environments, for example. And because Embeddings generation relies on heavy NLP dependencies and transformer models, maintaining runtime consistency across distributed Spark executors became, a major challenge in this project. And to solve this issue, I redesigned the runtime architecture using Docker and Amazon ECR. Okay, so this Dockerfile is quite simple. At the top of the Dockerfile, you can see that the image is based over here. Image is based on official AWS EMR serverless Spark runtime. This was important because it minimized compatibility issues between the custom container and the EMR execution environment. Next, well, the image installs all Python dependencies over here required for the embeddings pipeline. You can see this, that I have 3 requirements, takes the txt files, so for CI workload, for embeddings and general requirement file. And then here in the requirements embedding, we have sentence transformer, PyTorch, Pandas, PyArrow, Bot-of-3, and of course PySpark. Okay, let's go back to Dockerfile. Well, the next section copies the project's source code and put it directly into the Docker image. And as you can see, this the project code is stored under OPT recommender, and this location was intentionally selected because EMR serverless may internally use the app or app directory, right? And then over here, the image also configures environment variables such as Python path, PySpark path, Python, and PySpark driver Python. And this section, this environment variables configuration ensures consistent Python execution across Spark drivers and executors. Okay, and then we have one of the over here. Then we have one of the most important optimizations in this Dockerfile, because instead of downloading the embeddings model dynamically during runtime, the Docker image preloads and stores the sentence transformers model directly inside the container. And this approach significantly improves runtime stability and startup performance, for example. And as you can see here, the platform uses this all-mini LM L6 version 2 embedding model from sentence transformer library. Okay, and then we have this final section which configures file permissions and switches execution from the root user to the expected EMR runtime user, so Hadoop over here. Okay, and as I mentioned before, and as I showed you before, after building this image locally, it was uploaded to Amazon ECR, Amazon Container Registry, and then the embeddings pipeline then uses dedicated EMR serverless application configured to execute jobs using this custom Docker image over here. And we have here properties. And somewhere here we have this Docker image. Okay, it doesn't matter. It uses this Docker image, this EMR serverless application. Okay, to sum up this part, this architecture solved the earlier dependency and runtime consistency issues and created a much more production-oriented execution environment for distributed NLP workloads. And speaking of NLP workloads, now let's move to PySpark embeddings generation script. Okay, and this script is inside this source code folder. We have embeddings, and we have step 2, generate review embeddings. Okay, so okay, this script is one of the most important AI engineering components in this project. Basically, the input for this script is prepared review text dataset created in this previous pipeline step. So step 1, prepare and filter reviews. And the output is a Parquet dataset with generated vector embeddings stored in S3 bucket and S3 prefix. Okay, so at the beginning of the script over here, we have some libraries import, and as you can see here, some common functions import as well from this common folder, so some helpers, some utils. Then I establish over here a logger for monitoring the execution of the embeddings pipeline and capturing some events, warnings, or errors, of course, for troubleshooting and observability. Okay. Then the script defines the final output columns over here, including, for example, review ID, async, reviewer ID, some text hash over here, a model version, and of course a column with computed embeddings. And these columns are important because they support both downstream vector search, so this embeddings column, and some incremental processing. So for example, this text hash or review ID columns. Okay, then we have series of different functions in the script. First one over here, of course, the script creates a Spark session configured for the embeddings job. And then it builds here and here input and output paths, which dynamically get this path from environment settings over here. Okay. And then before generating embeddings, we have this validate require columns function over here. So before generating embeddings, the script validates whether all required columns are available. And this is, as a validation, it prevents the job from silently, producing incorrect outputs, for example, when the upstream pipeline changes, for example. Okay, so validate required columns. And then we have another set of functions. This function process batch. This one, well, basically this function performs the actual embeddings generation for a single batch of reviews. The logic is that it takes the clean review text, passes them to the sentence transformer model, then normalize the generated vectors, so over here, and creates the one output Spark row for each input review. For example, here, this zip function pairs each original review with its corresponding embedding, and then we have this loop, or loop for this loop, and then combines the original review metadata with the generated embeddings into a new Spark row, and finally this yield statement, instead of return, well, this yield statement returns one row at a time instead of building a large list in memory, and that is making this process more memory efficient and well suited for distributed Spark execution. Okay, so this is process batch function, and then we have this generate partition embeddings function over here. Oh, sorry. Generate partition embeddings. And this function is responsible for processing one Spark partition. Why? Because instead of loading the embedding model for every review, the model is loaded only once per partition, and then the reviews are processed in batches by repeatedly calling the process batch over here function. Okay, and then one last function before this main function. So transform function. Well, basically this function coordinates the distributed processing in Spark. Well, first it defines the schema of the output data frame. So here we have defined schema of the output data frame, including the embedding column, stored as over here as an array of floating values, and then it distributes the work across Spark partitions using this map partition function. So each partition is processed independently by the generate partition embeddings function. So this previous function, and finally this transform function converts the generated embeddings back into the Spark data frame, and returns the final set of columns that will be written to the output Parquet data set. So over here. Okay. One last function before main function. Basically, this generated embeddings are written back to S3 in Parquet format and partitioned by ingest date time. Okay, and at the end of the script we have finally we have this main function. So run generate review embeddings, and basically this function serves as an entry point for the entire Spark job. Well, it orchestrates the complete execution flow by loading the configuration, creating the Spark session, reading the validated input data, cleaning the transformation logic, and write it this generated embeddings into Amazon S3. Yeah, and finally, well, releasing cached resources and stop the Spark session. And one important thing about this main function, which I want to highlight, as you can see here, over here, I use this persist method on embeddings data frame object with storage level set to memory and disk, and I did it to cache the generated embeddings after the transformation step, and this prevents Spark from recomputing the entire embeddings pipeline multiple times when the data frame is reused by both this validation and write operation, because we have two actions here. so count and write. And as you probably know, Spark uses this lazy evaluation, meaning that the transformations are executed only when an action, such as count, for example, or write, is triggered. And since the data frame is used by these two actions in this function, so this persisting avoids executing the same, expensive computation more than once. And why did I choose the storage level for memory and disk instead, for example, memory only? Well, I did it because basically embeddings generation is computationally, very intensive, and the entire data set may not fit into memory. And if with these settings, if memory becomes full, Spark automatically stores cached partitions on disk instead of recomputing them. Okay. And finally, after the job completes, I call on persist over here, to release the cache data and free memory and disk resources before stopping the Spark session. So this solution in practice, this reduces execution time and probably saves some compute resources. And therefore it lowers the cost of running the job on EMR serverless application. Okay, so to sum up, this is like an example of major Spark performance optimization. Okay, so this is this generate review embeddings script. I think it's enough about the code. Now let's move to final data product demos. Okay, so now a very quick presentation of data products in this platform. Well, basically, I would like to show you 4 outputs of this project. First one is, of course, this ML-ready Iceberg tables. Then I will show you in my S3 bucket some Iceberg functionalities. Then, of course, Pgvector with semantic embeddings, so the semantic embeddings layer. And at the end, I will show you some JSON files with validation results, since validation is conducted after every step of this pipeline. Okay, and due to time constraints of this video, I will show you the final data products in a condensed version. For example, I will use SQL queries I have created earlier. I don't intend to write them during the recording of this video, like in this previous in my previous videos in my previous projects. Okay, so first data product is already Iceberg tables. And since well, data are stored in S3, but I use the Glue data catalog for schema and metadata. So I can query these tables through Athena once again. So this is my Athena database, ML ready, and then we have these four columns, for tables over here. And as I mentioned before, this project creates four Iceberg tables. So global stats, product features, user features, and user product interactions. And before exploring individual feature tables, well, first I first validate whether the ML-ready layer was generated correctly. So I have created this this query over here. And this query basically checks number of records across all 4 Iceberg tables. So we have one column table name, and then we have count as row count. And I union all these 4 results of 4 tables to see these results, well, all in one. Okay, so let's run this query. Okay, it's completed. And as you can see, the results, we have 4 tables and number of rows. Once again, I'm not going to analyze the results. I just want to show you that data are inside these tables and what kind of data, what kind of features, well, has been created by this this pipeline. And this first query, well, is simple but useful operational validation step, confirming that all downstream feature engineering pipeline steps have completed successfully, because we have well, a lot of rows in every table. Okay, next query over here. This one is like a simple quality validation query, and this query basically checks null values in key columns once again for every table. So to have these results in one place, I use this union all statement once again, and for every table I have count, so total rows, and this case when statement to sum some null values. And the key columns are asyn for product features, once again asyn for global stats and asyn for user product interactions, but for user features we have reviewer or user ID. Okay, once again, let's run this query and check how many nulls we have running. Yeah, it's complete. So as I mentioned, this query checks number of records across this number of null values for every key column. So there are no nulls, 0 nulls for in every table. Okay, and then to check what kind of information we have in every table, and to see if these tables contain engineered features optimized for downstream machine learning workloads, for example. Well, let's query each table separately. So let's start with product features. So I select all columns, and I order this query by just snapshot date, and of course I limit the results to 20. Okay, let's run it. Okay, and this is these are the columns of the first table. So product features. So we have different product features like asyn, title, brand, main category, price. And then to flag columns like has brand and has price, so the output can be true or false. Then we have description, total length, and feature snapshot date. Okay. Basically, this first table product feature table. It's a product level table used for recommendation and this potential downstream ML workloads. Okay, let's query second table. So this time user features. So now I selected all columns once again, but I use this where statement where review counts is equal or bigger than 5. Okay, let's query. Let's run this query. And once again, we have this user feature table with different columns, and these columns and this table is like user level aggregated behavioral feature table where we have, for example, average rating, average review text length, reviews counts, distinct product counts, and so on. Okay. Now, third table, global stats. Let's run it. Okay, and this global stats is like product level review statistics table where we have, for example, once again ASIN as a key value, reviews count, distinct reviewers count, average rating, rating standard deviation, and then we have some ratios like positive reviews ratio, negative reviews ratio, and verified reviews ratio. And we have different values of these columns over here, right? Okay. And one last table to go, one last query to go. User product interactions. Once again, I select all columns in this query. And I have created this condition where verified is true. And this is like interaction level table, which is joining user behavior, product metadata, and product review statistics. So let's run this query. And as you can see here, once again, we have some different features like user review counts, product price, product average rating, and so on. Review ID. And one additional thing about this data product, in my repository over here, project 3, I have in documents folder data products documentation, markdown fine, and this document describes this final data product. So this 4 ML ready tables, and for every table you can check over here the column name, column type, eventual unit, and of course description of every feature, every variable for all ML ready tables, and also for this vector review embeddings table over here. Okay, now let's move to Iceberg functionalities. And in this ML-ready layer, I used, as I mentioned a couple of times before, Apache Iceberg instead of plain Parquet files. Well, basically, Iceberg adds a metadata layer on top of S3 data files or stored data files in general. And this metadata layer tracks, for example, snapshots, manifests, schema information, partitioning, and table history. And thanks to that, the table then can support lakehouse features, different lakehouse features such as ACID transformations, snapshot in isolation, some schema, table schema evolution in time, and also some time travel. So getting information from the previous versions of the tables, from the previous schemas of the tables. Okay, but how does it look in practice? This Iceberg functionalities. Let's see my S3. And let's see my bucket, my projects bucket, project free recommender system bucket, ML ready layer, ML ready database, and for example, product features. And as you can see here, we have two folders here, one with data and one with metadata. Inside this data folder, we have this 25 Parquet files from one pipeline run. So these are actual data, but also we have this metadata folder, and inside this folder we have three files, one JSON and two other files. And this metadata folder is like a key difference between Iceberg and plain Parquet. Parquet stores only files, while this Iceberg tracks this metadata, allow you to track state, snapshots, and file manifests. So let's start with this JSON file. I'll probably open it. So let's move it to my VS Code repository, my project repository, and this is this JSON file. This file is basically the main Iceberg table metadata file, and as you can see here, it contains the logical definition and current state of the Iceberg table. And for example, here we can see, for example, physical S3 location, the complete, the table schema with all columns and data types. So here we have schema, and we have every column like ASIN, like title, brand, price, and for each column we have, if it's required, and data types. Has brand, has price, title length, and so on. Then we have also some compression settings over here. Current, this is very important, current snapshot identifier, so current snapshot ID, for example, here and here and here. Also timestamp, stamp in milliseconds, and some metadata about the latest write operation. So it's over here. latest write operation, like kind of operation, append, Spark application ID, number of added files, 25. We can check it's true over here, because here in this data folder we have 25 Parquet files. Number of added records, and so on, total file size, and different metadata about this latest write operation. Okay, and this metadata layer, the JSON file, is what enables Iceberg to support this Iceberg features. And then we have these two Avro files additionally in this metadata folder. Yeah, 1 and 2. And I can't open this Avro file directly in my cloud, so I have downloaded them into my repository over here and over here, and I have created simple Python script to open this Avro files with fast Avro library. There's basically a library for everything in Python. Okay, so this first Avro file, it's a snapshot. It's an Iceberg snapshot manifest list referenced by this metadata JSON file I've just showed you. Let's just run this query. I'm not going to analyze all these fields, all this data here, but this Avro snapshot file contains references to manifest files describing, for example, which Parquet data files belong to the snapshot, file level metadata, partition information, row counts, and so on, and some statistics, of course, used for query planning and optimization. Yeah, like over here. And then this last Avro file. Let's close this one. This Avro manifest. Yeah, let's run this script. And this is the last one with a lot of different metadata as well. And this last Avro file, it is actual Iceberg manifest file, and it contains once again metadata describing the physical Parquet data data files that belong to this current table snapshot. And this manifest stores information such as once again S3 file location, row counts, partition metadata, and file level statistics. For example, as you can see here, for every Parquet file, so for 25 different Parquet files, we have this statistics. For this one, then once again, for this one, and so on. Okay, to sum up this architecture, so data plus metadata allows Iceberg to effectively query very large data sets, without scanning the entire S3 storage layer. Instead of searching all files manually, the query engine can use this Iceberg metadata to identify only, for example, the relevant Parquet files required for successfully conduct a query. And as a result, this platform can safely manage large analytical data sets or big data volumes while supporting this transactional and scalable lakehouse operations. Okay, so to sum up, very useful features with Iceberg. Okay, now let's look at the vector serving layer built with PostgreSQL and this Pgvector. Basically, this layer stores semantic embeddings generated from customer review text with this 4-step, I think, pipeline, embeddings pipeline. And I will do several quick things with this table. So first, let's kill this. Let's kill this terminal. We don't need that. I'm still in my VS Code, and here I have this Pgvector, and I have prepared already this sample queries. Of course, I'm connected with my recommender database already. Okay, so first I validate whether the embeddings pipeline generated the expected number of vectors or review embeddings. So this is this first query. Let's run it with recommender. We have to wait a moment for the results. Okay, and we have results here. Basically, this query verifies, as you can see here, total number of embeddings, total number of reviews, a number of products, and embedding model versions stored in the system. And basically, the number of embeddings equals the number of reviews. So that's positive outcome. The same number of embeddings and reviews, because one review, one embedding. Okay. Next query. Well, this query verifies whether all embeddings were generated with the correct vector dimensions. So this one, let's run it. Okay, so we have 384 embedding dimensions, and we have row counts over here as well. And as a reminder, I use in this project all mini-LM L6 version 2 sentence transformers model, which generates exactly 384 dimensional vectors. So this query, this validation confirms consistency of this semantic vector space. Okay. Third query over here. We can preview with this query. We can preview metadata stored together with these embeddings. Okay. And as you can see here, this table stores not only vectors themselves, but also some metadata required for example, incremental processing, model versioning, traceability, and some future reprocessing workflows. So we have review ID, asyn, model version, text hash, and date of creation. And for example, this text hash helps detect changed review content. While this, for example, model version allows safe regeneration of embeddings after some, I don't know, for example, model upgrades, right? Okay, and finally, one last query with this CTE statement. Well, with this query, I can demonstrate like the core Pgvector functionality. So semantic similarity search. So with this query, I can find reviews semantically similar to a selected one. Let's run this query. Okay, and we have results. And as you can see here, this query selects one review embedding as a reference vector and compares it with other review embeddings using this cosine distance. So once again, we have review ID, async model version created and this cosine distance. Well, I'm not going to define this cosine distance. You can check it out. But basically, the lower the cosine distance, the more semantically similar the reviews are. So basically, we have these 10 reviews semantically similar to this selected review. And to sum up, well, this feature which I show by running this query, this is like one of the key building blocks behind, for example, semantic recommendation systems, semantic, I don't know, product search, RAG, or some AI agent knowledge retrieval systems. Okay, one last thing to show you, some validation results. To show this validation results, let's kill this terminal. We don't need this SQL script anymore. And I have these validation results in my source code, data validation, great expectations results. Well, and inside here we have like JSON files for every validation step. In general, I use in this project great expectations for validation, together with some custom validation logic to verify data the quality after some major processing stages. Validation in general is executed for staging data sets, for ML ready feature tables, and once again for vector embeddings. Okay, and as I mentioned, these validation results are stored as JSON artifacts. Let's see one of them. So for example, validate ML ready product features. It's really long, as you can see, really long JSON file. Okay, and in this example, we can see the validation results for ML ready product data set, and this validation checks include, for example, null validation for business keys. So we have null validations over here, uniqueness validation, some schema, and data type validation, require column existent checks, and for example, completeness checks for semi-structure attributes such as categories. Basically, here we have the entity, then execution date, then we have this table name, and then we have expectations, so basically tests. And each expectation contains, well, first of all, validation status, so success, true or false. Then some severity level, like critical in this case. And then some row statistics, results over here, and some detailed validation metadata over here. And then we have another expectation and another expectation, and so on and so on. So different expectation and different tests. And for example, here at the beginning we can see that the async column, so we have this column async here and also here. So this async column passed both not null validation. This was like this first test, first expectation, expect column values not to be null, and uniqueness validation. So the second expectation, so expect column values to be unique. And as we can see here, with 0 unexpected values detected over here and over here. And we have this expectation for other columns and other kind of tests, right? For example, expect column to exist, expect column values not to be null, and so on. Expect column values to be between. So different expectations and different kind of tests. Okay. So once again, this great expectation framework is very useful for data engineering, data science, and so on. Okay, to sum up, this platform produces two key data products. ML-ready Iceberg feature tables for some analytical or machine learning downstream use cases, and validated vector embeddings stored in this Pgvector for semantic retrieval and AI-powered applications. Okay, now let's sum up this video. Okay, to summarize, this project is by far the most complex and complicated one in my portfolio. And for the first time, I try to create data system for AI use cases. I really hope I demonstrate how to build a modern recommendation system oriented data platform using both cloud native and scalable technologies, including open source frameworks like Airflow, Apache Spark, or Great Expectations. And one of the most important lessons from this project was understanding how dependency management and runtime consistency became critical in distributed cloud environments. And trying to run PySpark Embeddings generation script on AWS EMR without Docker image was, well, a pain in the ass, and it took me several hours to fail, basically. Okay, and at the same time, I'm aware that this project still has some limitations. For example, the platform uses batch processing instead of streaming, and the most effective recommender system would suggest additional items or products to buy up to date. Well, second, recommendation models themselves are not implemented yet. This is more task for data scientists or ML engineers. And well, the orchestration strategy prioritizes stability over maximum parallelization. Okay. Well, however, those decisions were intentional and aligned with the project scope, infrastructure constraints, and some cost optimization goals. Okay. Overall, this project allowed me to simulate a realistic production-oriented data engineering environment for modern recommendation systems. I hope you like this video, and by the way, I would like to invite you to watch my fourth video on which I'm currently working. My next data project is about creating data system for computer vision use cases with Databricks platform this time. Okay, so thanks again for watching.